So by using closure and by using function scope, we can create modules in this language. So suppose I want to make an object which will have two methods in it. And those two methods will have access to shared private state. We don't want to put that shared state in global variables because that's obviously problematic. So instead, we'll have an outer function in which we'll declare all of that stuff, and then we will return an object. This is the object literal notation, a brilliantly expressive way of initializing objects in this language. And these two methods will both close over the private stuff. Okay, so as long as either of these methods survive, then that material will survive. Now you could look at this and go, well, we could generalize this version and do it not just once, but call this function over and over again and make lots of stuff. So let me give you a recipe for a way to make resilient objects in this language. So step one, we make an object using any of the techniques available in the language for making objects. Step two, we define some variables and functions. These will become the private members and private methods of our object. Step three, we augment the object with privileged methods. A privileged method is a method which has access to that private material. And step four, we return the object. So pretty simple, but a little abstract. So let me turn it into a template to make it easier to follow. So step one, I've got my power constructor. It takes x as an argument. I create a variable called that and initialize it somehow. In this case, I'm calling some other constructor which will make stuff for me, which actually gives me another dimension of inheritance. I'm calling it that. I'd like to call it this, but this is a reserved word, so I'm going to call it that. And then step two, I can create my secret variables, and I can initialize them now, or I can initialize them later. And step three, I add my privileged methods to that. And the privileged methods will close over the secret variables that I created, over the parameters that were passed into the constructor, and to that as well. Everything that's inside this function is available to these functions. And step four, I return that. That's it. So a very simple pattern. You can make powerful objects in this, and it's really easy. So you've got functions making objects containing methods. This all works because of closure. A function is a thing which is executable, but it is also the context of the function in which it was created. So because it has that context, it has access to all that other material. It's kind of a shame that it's called closure. I mean, it makes sense, but most people think of closure as meaning retribution or vengeance. And this doesn't mean that. This is a completely different concept. So writing in ECMAScript without understanding closure is like writing in Java without understanding classes. It's possible to do that. You can write in Java like it's Fortran, put everything in main, but it's not a good use of the language. Similarly here, if you don't understand closure, if you don't understand how functions work, you're not really writing JavaScript. When we write in the browser, we have a model of programming called turn-based computing. A turn is started by an external event like the clock or an incoming event or a user interaction, something like that, which will cause some function or callback that was associated with that event to be called. That function will then run to completion, and only after it completes does the next turn start. The next event can be dispatched and so on. It's guaranteed that no other event will start up until the current turn is finished. So races and deadlocks are completely avoided. So it turns out to be a much simpler model. It avoids the hazards that you have in thread-based systems. And so for this reason, I expect we will never have threads as a part of this language, which is a good thing. But the trade-off is that you have to obey the law of turns. The law of turns says, never block, never wait, finish fast. In some programming environments, this is an alien idea because you'll be sitting in loops polling for things. And you cannot do that in a turn-based system. That's not allowed. Now, if you have asks, they're clearly not well suited to a turn-based system, but even then there are some alternatives. One is a technique called ecursion, where you take a long-running process and break it up into separate steps and do one step per turn. And at the end of each step, it will program an event to cause the next step to be taken. So you may still take a lot of time, but it happens in small discrete turns, which allows the system to remain responsive. The other technique is to move the task into a worker. Google did some really good work with Google Gears and Google Chrome, in which you have workers which are separate threads, separate memory, where you can safely have programs run, and then when they're complete, they can mail the results back. So that starts to look again like the actor model, which is actually a brilliant way to do things. Now we're starting to do a lot more JavaScript on the server now. Node.js is a very powerful way of doing HTTP service using JavaScript on the server side. And it wants to be turn-based as well, so that we've got exactly the same model at both ends of the network, which is really attractive. But in server applications, it gets more complicated because you can have more dependency on the requests. For example, in building a web page, you might go out to 20 different services, and then you want all of those requests to come back. In a turn-based system, it's easy to make all those requests in parallel. So instead of paying for the cost, the additive cost of all those requests, you're only paying for the longest one, which would be much shorter. But you have to deal with the synchronization of all of those different events coming back at different times. There's also a situation where you might have a sequence of queries you have to do before you're done assembling the page. For example, I have to look this up in a user database, and then I have to go look that up in a different database, and look that up in a different service, each of these depending on the result of the previous one. The naive way of doing that is to have deeply nested callback functions. And that turns out to be very brittle and very difficult to maintain, so that's not good either. So I've been looking for ways of using the power of JavaScript to deal with that. And one technique that's available is requesters. So I'm proposing that any request that we're going to make of an external service within the server, we represent it as a function, because functions are the solution to all problems. So I'll create a requester function, which will take a sync function as an argument. We'll get to that in a moment. And it will call some service. It might be XML HTTP request or some other way of going someplace to get information. And it takes parameters. And we pass also a callback function. And the callback function will be called when the result is known. And the callback function I'm proposing takes two parameters. One is the success parameter, the result parameter, and the other is the error parameter, or the failure parameter. This is important because exception handling doesn't work in a turn-based system. Because if you look at what exception handling does, is it unwinds the stack. But in a turn-based system, the stack goes to 0 on every turn. We throw the stack away and reuse it on the next turn. So there's no way to throw an exception into a previous turn. There's no way to get there. So instead, we do exceptions with callbacks in the same way, and there's no problem using one function to handle both the successful case and the failure case. Now you might be looking at this and go, oh, wait a minute, this is too much work. I now have to write two functions every time I want to ask for something. Okay, but point taken. So the solution to that is to create another function. So, so I now have a request maker. And I call the request maker, and I simply pass it the parameters, and it returns a requester function for me. Okay, so problem solved. So this actually makes a nice API for making requests. So what good does that do? Well, because I can now easily make these requester functions, I can now compose with them. So I could have a parallel function, which takes an array of requester functions. And it'll go and call them all at once and get everything started. And it will keep track of all of them finishing and all the results. And when all of them are done, it will then call the sync function that it was supplied with. And it can also do extra processing like dealing with timeouts. You know, if the whole thing takes too long, we can have it produce an error for us so we can get out of it early. Or if I want things to happen sequentially, I can pass an array of these requester functions to a sequence function. And it will call the first one and get its result and pass the result to the second one and pass its result to the third one and so on. So again, I can compose this thing really easily. A map function does the same thing, except it returns an array containing each of the results that it accumulated. For some applications, that's the ideal way of dealing with this. And then we can go even further. I can have functions which return functions which will have done those things. Okay, so I can produce a parallel requester which could take a bunch of sequential requests, and I can build sequential requests with that. So it gives us composition, so we don't have to be deeply nesting things. We can talk about all these things sort of discretely and then combine them in powerful ways. So I'm going to talk a bit about Thompson designed B, and Ritchie took that design and designed C. They put the curly braces on the right. And there were people in their lab who said, no, we're not going to do that. We're going to put them on the left. And Thompson and Ritchie said, okay, leave us out of it. We don't want to get in this argument, which was wise, but I think in the end they did us a disservice, because even today we still don't know. Should you put the curly braces on the left, or should you put them on the right? What you can get people to agree on is you should all do it the same way. And generally you can get anybody to agree, everybody should do it the way I do it. But whether you do that or not, you should at least be consistent. It's sort of like driving. There's not a good argument for why we should drive on the left or on the right, but it's a really good idea that we all be on the same side. And this isn't quite as critically important as that, but it's sort of the same thing, because people will get really passionate about what side they're putting their curly braces on. And if you tell someone who puts them on the left, no, from now on you're putting them on the right, they'll cry. And they will come up with these amazing reasons for why the left is the right way to do it. And part of the reason why they're crying is because deep inside they know their arguments don't make any sense. There is not a good reason for why you should prefer one or the other. Unless you're working in JavaScript, in which case you want to always put them on the right and never on the left, and I'll tell you why. So earlier we saw a case where we return an object literal. This turns out to be a very common, important pattern in JavaScript. And if you put the curly brace on the right, it does the right thing. And if you put it on the left, it does one of the worst possible wrong things. Instead of returning your new object, it returns a value called undefined. And it doesn't give you any warning. There's no compile warning, there's no runtime warning, it simply returns the wrong value. And if you're trying to debug this thing, you're going to go crazy, because the point at which your program fails is not going to be at the site of this return statement, it's going to be someplace else. And you're going to be tracking around, and eventually you might trace it back to this code, and you're going to look at that for hours and not see what went wrong. This is one of the hazards of JavaScript. There's a feature called automatic semicolon insertion, which was intended to help beginners to not have to understand C syntax, which is unnecessarily complicated. And so it'll put semicolons in for you, except it sometimes doesn't put them in places where you would expect, and it sometimes puts them in places where it shouldn't, and this is one of those times. It'll put a semicolon after the return. So this changes from being a statement that returns a useful object to a statement that does nothing, that returns nothing. So because of this, I say, always put them on the right. I mean, the difference in cost, if you look at how much does it cost to have braces on the left versus on the right, turns out it costs the same. I mean, there's no economy that says you want to be doing it on the left. And if you always put them on the right, this error will never happen to you. So that's easy. So that's part of the philosophy of having good parts. Here's another example. This is I've seen people cry about this too. So the problem with this statement is it's visually ambiguous. I've seen people who expect it to do what the red statement says, but it actually does what the green statement says. So it does not declare a variable called B. It instead zeroes out a global variable called B. which is confusing. So when you're reading this program and you see a statement like that, which one does it mean? And it's impossible to know for sure. So you don't want to be putting stuff like this into your program, particularly when there's a more correct way of writing it. There's no reason to ever do it the wrong way. Here's another one. This is another defect that was inherited from C. It looks like it means this, but it actually means that. And so there is a visual ambiguity, and I've seen cases where maintainers of programs not recognizing the hazard would add a C to something and change the meaning of the program in a nasty way. So the thing you might learn from that is always put the braces in. It's just 2 characters. And I've seen people cry when you say you got to put them in. So that statement, it's 2 characters. You know, the cost is negligible. The return on that investment is huge because it means your program is going to be more resilient, but it's much less likely that someone's going to be practicing this bug on it. Our whole reason to exist is to try to minimize our failure rate. And so there are simple things we can do in selecting the subset of the language that we're going to use that can help us do that. So it should be clear from reading the program what it actually does. And we should be avoiding forms that are difficult to distinguish from common error. But this one is more controversial. So it was intended to facilitate pointer arithmetic. And it was implicated in most of the operating system buffer overrun security hazards that we experienced over the last couple of decades. So in my own practice, I just don't use it anymore, ever. When I used this, my code would always be too tricky. I'd be trying to get too much stuff happening in one line, and I was always obscuring my intent. So I believe that since I stopped using it at all, my programs have gotten cleaner and easier to read and easier to manage. And I've seen people get really upset about that. You know, so I write this instead. I say x plus minus 1. That's just fine. It costs me, what, an extra character. I think that's a good value. But still, people write to me and say, I like writing it this way. But in fact, this is wrong, because the thing they intend was this, right? And the fact that you've got this dyslexic thing going on with plus plus is a whole nother set of hazards. It's really easy to get the pluses on the wrong side, and the errors that result from that can be really difficult to find, and you completely avoid all that hazard by just using pluses. So again, these are all small things, but I think overall they have big rewards. So it's sort of like writing with scissors. You know, they teach you when you've got scissors, you hold them like that, and you walk carefully so you don't stab yourself or others. But I hear from people all the time saying, I should be able to take the scissors and run like that. See, I'm not hurting anybody. And you know, my argument is not that every time you use plus plus you're going to kill somebody or put your eye out or your sign. We're just trying to improve the odds in our favor so that we can be writing stuff that's more correct, and making fewer mistakes is a good thing, not a bad thing. Yeah, so the argument that hardly ever happens, that's just another way of saying it happens, except that it's easier to draw incorrect implications from that. It happens. Bugs happen, and that should inform the way that we program. There will be bugs, so we want to do things to move the odds in our favor. So to help you do that in JavaScript, which is especially critical because there are so many errors and hazards in JavaScript, there are way too many. I wrote a program called JSLint. JSLint knows about the good parts and it knows about the bad parts, and it will read your program and tell you about all the bad parts. So you shouldn't savagely replace them. For example, if it sees you're using double equal, it'll say that's a problem, you should be using triple equal. Don't just go and rep for double equal and change them all to triple equal, because that will probably insert bugs into your program. It's important to understand what your program was trying to do and then put in the correct operators. But if you do that, if you take JSLint's advice, your programs will get better. And it's free. You can go to jslint.com and here it goes. One warning, JSLint will hurt your feelings. It's true. It's mean. It is a mean program, and it's vicious. And it will tell you exactly what's wrong with you and your program. And my advice is do everything it says, because it's smarter than me about JavaScript. It truly is, and it's probably smarter than me too. So why do people cry about this? And they do. I think it's because unlearning is really hard. Once it gets in there wrong, it's really hard to get it out. Even though programming is one of the most, requires more intelligence, I think, than just about anything else that humans do. A lot of it happens in the gut. And most of the decisions we make about technology and programming style happens in the gut and not in the brain. And so when we're presented with ideas which can make our lives better, our response isn't gratitude, our response is resentment and anger and denial. I remember when it happened to me, there was a beautiful book that was written by Kernighan and Plowger called The Elements of Programming Style. They did this amazing thing. They went through a whole bunch of other textbooks and took the example code out of those textbooks and showed how they were wrong and rewrote them correctly. Really audacious book. And they got permission from all those authors to do that, which was kind of amazing. And at the time they were, the language of the day was Fortran. So that's why the book's not in print anymore. It's still a brilliant book and worth reading. But in Fortran, Fortran was designed for key punch systems, for punch cards. So the format of the statement was columns 1 through 5 were where you could put a statement number, and columns 7 through 72 were where you could put the statement. And 73 through 80 were where you put the sequence number. So when you dropped the deck of cards, you could throw it in this order and maybe get it back in order. And then if you had a statement that didn't fit between columns 7 and 72, you could put it on the next card, and you put a punch in column 6, which said this is a continuation. And Fortran allowed you to put any character other than space into column 6. And so there were different conventions. There was one that said you'd put a number for the one for the first one, 2 for the second one, or maybe A for the first and B for the second, and so on. But the authors of this book said, well, we looked at the character set that comes with Fortran, and there's only one character in the character set that isn't actually used as an operator or anything else, and that's the $. So we're going to use $, in the continuation column because it doesn't go anywhere else. If you put a plus in column 6 and you actually punched it wrong and you got it in column 5, it's going to alias to a statement label. If you put a letter in the other one, it might be aliased as a variable name. But $, there was no ambiguity. If you got the wrong thing, it's going to be a syntax error either way. And it was brilliant. I mean, it was simple, it was bright, and it made me mad as hell. Because, at a deep level, I wished I had thought of it, and then I realized I hadn't, and I was going to have to go back and repunch all those cards, and it just made me mad. So I understand why people get upset when you talk about programming style, because it's here, it's not here. Somehow, when you're getting mad about these things, you're not thinking, you're feeling. So that's where that comes from. Yeah, so people write to me all the time and they say, what I'm doing is perfectly fine. They always say that, perfectly. Perfectly is not a brain word, that's a gut word, for sure. Yeah, so. One other reason for why you should be considering JavaScript is that it has become the virtual machine of the web. This is a surprise. Nobody expected this result. I always thought that the Java VM was going to be the VM of the web. But it's not. Google is now translating Java into JavaScript so they can run it everywhere. That's an amazing thing. C# is now being translated into JavaScript so it can run everywhere. People are designing whole new languages to compile into JavaScript. Wow, I mean, this is a wild thing. JavaScript was not intended for this purpose. In fact, some of its features are fairly poorly considered for this role, but yet this is a role that it has found itself in. Let me leave you with a research agenda. There's still a lot of work to be done around JavaScript and web systems, and we need your help. So the number one problem we still have in the web is security. The browser is actually closer to being a secure platform than everything else. It's the most secure application delivery system we've ever seen, but it's not good enough yet. And JavaScript is actually surprisingly close to being a secure programming language, especially with ECMAScript 5th edition strict code. It's almost a secure programming language, which is an amazing thing, but it's not quite there yet. So we need some more work there. We need a lot of help with performance. For a decade, we had very slow JavaScript engines. All of the engines were optimized for time to market decades ago. Just recently, they've started competing for speed, and they're actually getting quite fast. But they're doing heroic things in order to get things going fast. And we're seeing more and more JavaScript is moving to low-power environments like mobile devices. And those heroic actions actually work against us there because we're draining battery time. So we need to be thinking better about efficiency in these implementations. We also need better benchmarks. The standard ways that we measure JavaScript performance don't work. There was a really good paper from Zorn and Lifshitz of Microsoft Research last year, which showed that the popular JavaScript benchmarks have no correlation with real web applications. The benchmarks are not at all predictive of how actual applications work. Despite that, all the browser makers are tuning to the benchmarks, because right now they're all trying to get the best numbers. And they don't care that the numbers are bogus, they just want to get the numbers. So we need better benchmarks. So I just published one today. I'm using JSLint as a benchmark. JSLint is written in JavaScript, so I have JSLint test itself and then report its elapsed time, and I run that against all the browsers. And by my metric, right now the fastest JavaScript engine in the world is the one that's in IE 10 preview. And the slowest is Google Chrome, which was a big surprise. It's about 5 times slower than the Microsoft one. The people at Microsoft right now believe that Chrome is kicking their ass because it's doing better on the benchmarks. But by my measure, IE 10 is doing better in reality, which is where I live. Anyway, we need better benchmarks. We're now seeing a big push of JavaScript moving back to the server side. And there are amazing opportunities there, new application deployment models and lots of stuff. I think the actor model is really important, and JavaScript is a useful language for implementing actors, and the term application system is very actor-like. But I think there's a lot more to be explored there. Actors are brilliant for doing concurrency, both at very large scale in distributed systems, and perhaps also a very small scale, solving the multi-core problem. Decimal arithmetic. We're really hurting for not having the right number type in this language. IBM tried to force us to adopt IEEE 754R, which is a decimal revision of the earlier format. In current implementation, the browser makers refused to accept it, because in this race to try to look faster, they weren't going to accept anything that might make them look slower, even if it turns out that almost all of the arithmetic we do in JavaScript is integer, and so you can factor that out anyway. So we need a more credible decimal format. We need better tools for JavaScript. Because of JavaScript's loose typing, the IDEs have trouble understanding it and helping us to sense things and fill in and complete things. So we need some more research there. I think having useful type checking applications to help us in designing programs and testing programs. JSLint only looks at the surface syntax of things and can't look deeply. I think tools that did a deeper analysis could be extremely useful. Testing is difficult in JavaScript. System tests are really easy, But unit tests are really hard because we've got all these deeply nested functions. You can't pull a function out of a nest and test it independently. That doesn't make sense. It needs the stuff that it closes over in order to be useful. We don't know how to test that stuff adequately, so there's some opportunities there. Finally, we need a new DOM. When most people who use JavaScript say they hate it, what they're really hating is the DOM. The DOM is the API that the browser provides for manipulating the document object model. It is a terrible thing. It's at the wrong level of abstraction, it's inconvenient, it's buggy, it's not portable, it's the source of most of our pain and misery. And we need to replace it. It's also horrendously insecure. So we know how to replace it. If you look at any of the AJAX libraries, like YUI or jQuery, they turn the DOM, by hiding it, into something that's pleasant and productive. And a surprisingly small amount of JavaScript is adequate for doing that. Because JavaScript is such a powerful language that it can turn the worst API into something that's nice. So my belief is that the native API should be that. It should be the thing that jQuery or YUI is providing us. So I would like to see us eventually design and formalize and adopt that. So that's all I've got for you tonight. I think JavaScript is, my thinking about JavaScript has changed a lot from when I started. The first impression, when I saw the first announcement from Sun and Netscape for JavaScript was, this is the stupidest thing I've ever seen. And I held close to that opinion for 5 years. And then circumstances forced me to actually try using it. And like everybody else, I started without learning it. And I found that to be an incredibly painful experience. It would roundhouse kick me in the head all the time, and I got really tired of it. And then eventually I decided to try to read the standard and find out what this thing actually was. And the standard, I'll warn you, is really difficult to read. The latest edition is an improvement, but it's still much too difficult to understand. But in thinking deeply about what was in it, I made a discovery, which was there are lambdas in it. It's full of lambdas. This turned out was the first important discovery of the 21st century, that JavaScript had good parts. And that started changing my relationship with the language. At last I understood what it was about and how to use it. But I was still really angry about all the bad parts. So if you read my book, JavaScript, The Good Parts, it's a really angry book. I'm completely unforgiving of all of that bad stuff that's getting in the way of all the good stuff. Since then, I've mellowed a bit. JSLint has gotten to the point where the bad parts don't touch me anymore. I'm pretty much immune to that. So I'm only working in the good parts now. And they are really good. They have deeply changed the way I think about programming. And I really enjoy it. And I've come to a really unexpected place where I now believe that JavaScript is not just a good language, it's actually one of our best languages. And that's a result that I never expected. But that's what I wanted to share with you tonight. I think JavaScript is worth your study and interest. Thank you very much.